Thanks, Craig. Boy. So, as Craig told you, my name is Aater Suleman, and I will be talking about feedback-driven threading. It is a mechanism to enable high performance and low power execution of multi-threaded workloads on CMPs. I did this work at UT Austin with Moinuddin Qureshi and my advisor, Yale Pat. So to improve the performance of a single application using multiple cores, the application must be divided into threads. Threads improve performance by splitting the work to be done in multiple portions and executing them simultaneously on multiple cores. With the number of cores increasing, an important question is, how many threads shall we execute simultaneously? There are some applications which scale very well. For these applications, we should use as many cores, as many threads as there are number of cores on the CMP. But there are other applications which do not scale. Their performance saturates. And for these applications, we should have fewer threads than there are cores. Because once the performance has saturated, adding more threads does not help performance and increases power consumption. Therefore, the number of threads must be chosen carefully. There are two important limitations which lead to this saturation of performance: contention for shared data and contention for shared resources. Contention for shared data occurs when programmers use critical sections to synchronize accesses to shared data. The semantics of a critical section dictate that only one thread can execute it at a given time. Let's look at an example. Here is a kernel from data mining workload PageMine. This kernel computes a histogram. It counts the number of times an ASCII character occurs on a page of text. The histogram has 128 buckets, one for each ASCII character. This kernel can be parallelized such that each thread can execute and compute the histogram for a separate portion of the page. And these histograms can then be combined to generate the final histogram. This kernel has two parts. In the first part, threads compute their local histograms in parallel. And in the second part, threads update the global histogram. This update is protected by a critical section, and thus has to be done serially. Once all threads have finished updating the global histogram, they stop at a barrier before they can start processing the next page of text. For simplicity, let us assume that if only one thread is used, this kernel takes 10 time units to execute. 80% of the time is spent outside the critical section, and 20% of the time is spent inside the critical section. With two threads, the time outside the critical section decreases because now each thread has to process a smaller portion of the page, while the time inside the critical section increases because more updates have to be done to the global histogram. With four threads, the time outside the critical section further decreases, and the time inside the critical section further increases. And the overall time, in fact, increases from 8 time units to 10 time units. And with 8 threads, the execution time further increases to 17 time units. Thus, if we continue to add threads once the performance is saturated, the additional threads not only increase the power consumption, but they also increase the execution time. Contention for shared resources occurs when multiple threads try to access a critical resource frequently. One such resource is the off-chip bus. Let's look at a numerical kernel ED. This kernel computes the Euclidean distance of a point from the origin in an n-dimensional space. The kernel streams through the array A, which makes it bandwidth intensive. This kernel is parallelized such that multiple iterations can execute in parallel, which further increases the demand for off-chip bandwidth. Again, for simplicity, assume that this kernel accesses the off-chip bus once every 4 time units. The bandwidth utilization is 25%. With 2 threads, the execution time decreases, and the bandwidth utilization increases to 50%. With 4 threads, the execution time further decreases, but the bandwidth utilization has now reached 100%. And once the bandwidth is saturated, increasing the number of threads from 4 to 8 does not result in reduction of execution time. Thus, for workloads which get limited by bandwidth, once the bandwidth saturates, adding more threads does not impact the execution time, but still consume power. We have shown that the number of threads impact both performance as well as power. The next question is, who chooses the number of threads? Is it the one who writes the application, or is it the one who uses the application? For general purpose applications running on desktops, neither is feasible. It is difficult for the programmer because there is large variation in the input set and machine configuration. And it is difficult for the user because they are not experts. I don't know about you, but I don't like my media player to ask me the number of threads I want to use. And when both the user and the programmer does not specify the number of threads, a common strategy is to set the number of threads equal to the number of cores, with the implicit assumption that more threads lead to more performance. As we have just seen, this is not always the case. So what we require is a runtime mechanism which can estimate the number of threads at runtime without requiring intervention from the user and still takes input set and machine configuration into account. As a solution, we propose feedback-driven threading. First, I will describe its model. Let n be the number of threads and k be the number of cores. In conventional threading, we will set n is equal to k. On the other hand, in feedback threading, we set the number of threads at runtime. We do this in 3 steps. First, we execute a small portion of the kernel to analyze the application behavior. Then we choose the number of threads using this information, and the rest of the kernel executes with that many threads. Feedback-driven threading is a generalized mechanism. It can be used to handle several different types of workloads. We limit the scope of our work to 2 types of workloads, which are limited by synchronization, similar to the kernel I showed you earlier, and limited by bandwidth. First, synchronization-aware threading. Recall that for workloads limited by critical sections, as the one we saw earlier, as the number of threads increase, the time outside the critical section decreases, and the time inside the critical section increases. We can capture this using a simple analytical model. The time taken to execute the kernel with n threads is a sum of the time outside the critical section, which decreases linearly with n, and the time inside the critical section, which increases linearly with n. If we take the first derivative of this equation and equate it to 0, we find that execution time minimizes when the number of threads, NCS, is equal to the square root of the time outside the critical section divided by the time inside the critical section. This implies that even if only 1% of the time is spent inside the critical section, performance saturates at 10 threads. We can implement SAT using the feedback-driven threading framework. During train, we measure the time inside and outside the critical section. This can be done with the help of the cycle counter register, which exists on most modern processors. Then the number of threads is computed using the analytical model, and the remaining kernel executes with that many threads. Before I show our results, I will describe the methodology. We simulate a CMP with 32 cores. Each core is in order and has a 5-stage pipeline. The cache hierarchy includes a private L1 and L2 and a shared L3 cache. The off-chip bus is 4x slower than the core frequency, and we simulated all queuing delays. Here we show the execution time of 4 synchronization limited workloads. The y-axis is the normalized execution time with respect to one thread, and the x-axis is the number of threads. In each case, the blue dot represents the number of threads chosen by SAT. In case of PageMine, performance decreases until 4 threads and begins to increase beyond 6 threads. SAT shows 7 threads, which is close. Similarly, for iSort, gsearch, and EP, the number of threads chosen by SAT is close to the optimum number of threads. Thus, if instead of setting the number of threads equal to the number of cores, we use SAT to choose the number of threads, we can save power as well as execution time. The time inside and outside the critical section is typically a function of the input set. For example, for the kernel PageMine, the best number of threads changes with the size of the page for which the histogram has to be computed. As we change the page size from 4 kilobytes to 24 kilobytes, the best number of threads varies from 3 to 14. Since SAT is a dynamic mechanism, it can adapt to these changes in the input set. We show the results for 2 cases, when the page size is 2.5 kilobytes and 10 kilobytes. As you can see, in both cases, SAT successfully predicts the best number of threads. Not all workloads are limited by data synchronization. There is another class of multi-threaded workloads where threads share minimal data. For such workloads, there is a large tendency to get limited by off-chip bandwidth. For these applications, we propose bandwidth-aware threading. Recall that once the off-chip bandwidth has been saturated, more threads do not provide any benefit in terms of execution time. If we assume that bandwidth increases linearly with the number of threads, we can develop a simple analytical model. That is, the bandwidth saturates when the number of threads, NBW, is equal to the total bandwidth divided by the bandwidth used by a single thread. We can implement BAT similar to SAT using the FTT framework. During train, we measure the bandwidth utilization using the performance counters that already exist on modern processors. During compute, we use the analytical model to compute the number of threads required to saturate the off-chip bandwidth, and the remaining kernel executes with that many threads. Here we show execution time of 4 bandwidth-limited workloads. The y-axis is the normalized execution time with respect to one thread, and the x-axis is the number of threads. The blue dot represents the number of threads chosen by BAT. In case of ED, the bandwidth utilization is 14% when a single thread is used. Therefore, BAT predicts 7 threads, which is close to the number of threads required to saturate performance. Similarly, for convert, transpose, and mTwister, the number of threads chosen by BAT are similar to the number of threads required to saturate performance. So if we use BAT to choose the correct number of threads, instead of setting the number of threads equal to the number of cores, we can save power by turning off the cores without impacting the execution time. We showed that BAT can predict the best number of threads for a particular system. BAT is also robust to changes in machine configuration. Here is an example from benchmark convert. We simulated it with half the bandwidth and 2x the bandwidth of the baseline. When the bandwidth is halved, the best number of threads for convert is 9, which is successfully predicted by BAT. And when the bandwidth was doubled, the performance did not saturate until 32 threads, which was also successfully predicted by BAT. Thus, BAT is robust to changes in the machine configuration. SAT and BAT can be combined for greater benefit. During train, we train for both SAT and BAT then the number of threads is computed as the minimum of NCS, NBW, and the number of cores. And the remaining kernel executes with that many threads. This graph shows the execution time and power for SAT plus BAT normalized to the case with 32 threads. Workloads are split into 3 categories. For synchronization limited workloads, SAT plus BAT reduces both power as well as execution time. For bandwidth limited workloads, SAT plus BAT reduces power without impacting the execution time, except in case of convert. In convert, having too many threads causes thrashing in the cache. So when we choose a smaller number of threads using SAT plus BAT, we actually not only reduce the bandwidth requirement, but also reduce the number of cache misses, which leads to savings in power as well as execution time. As you can see, for scalable workloads, SAT plus BAT did not impact power or execution time. And on average, SAT plus BAT reduces the execution time by 17% and the power in the cores by 59%. We also compared SAT plus BAT to a static best scheme. To implement the static best scheme, we simulated all possible number of threads and chose the best number of threads. The first 2 bars show the execution time of SAT plus BAT and static best, and the next 2 bars show the power of SAT plus BAT and static best, respectively. All values are normalized to the case with 32 cores. As you can see, the execution time with SAT plus BAT and static best are within 1% of each other in all cases. Similarly, the power of SAT plus BAT and static best are similar in all cases, except for M-twister, where SAT plus BAT saves 34% more power than the static scheme. This is because M-twister includes 2 kernels. The first kernel saturates at 12 threads, while the second kernel takes advantage of all 32 threads. Static best scheme chooses 32 threads for the whole program because the execution time continues to decrease. SAT plus BAT chooses 12 and 32 for the 2 kernels respectively, which decreases the power without impacting the execution time. Other researchers have also observed that more threads do not lead to more performance. There is a whole body of knowledge in the SMP domain, which we describe in the paper. I will not go into the detail in the interest of time. But the work which is most closely related to ours is the work by Lee et al. They propose a mechanism to control the number of threads at runtime for a CMP system. However, there are 2 key differences. First, their goal is to minimize power for a given performance target, whereas FDT targets both execution time as well as power. Second, they use a hill climbing algorithm, which requires that the kernel must be invoked multiple times, where FDT does not have any such restrictions. We have shown that FDT is an effective mechanism to estimate the best number of threads at runtime. Feedback-driven threading saves power and reduces execution time, and it is robust to changes in the input set and machine configuration. Moreover, it does not require effort from the programmer or intervention from the user. Thank you very much for your time, and now I will take any questions.
When you come to ask questions, please state your name and affiliation.
Hi, Lucas Krieger Stickles, University of Washington. This is really interesting. I was curious, the kernels that you mentioned seem to all be of the flavor parallel compute serial update of some shared resource. But that obviously is not the entirety of multi-threaded workloads. There are certainly flavors of multi-threaded execution where you have parallel computation interspersed with access to critical sections, which would allow the critical section that was being accessed by one thread to be co-located in time with parallel computation by the other threads. Did you consider any workloads that had that flavor, and how would that affect the accuracy of the model that you use?
So as I mentioned in the presentation, we kind of limited the scope of this study to the kind of workload, the example that I showed earlier. But we have certainly thought about the workloads where critical sections can actually be executed simultaneously while there is other work going on. And I have some ideas on how such workloads can actually be catered using feedback-driven threading. We can discuss it offline if you're interested.
Thank you.
You're welcome.
Cliff Click Azul Systems. Let me first state that your core counts and sizes look very reasonable to me, in that every one of your numbers for your CPUs was within like a factor of 2 of what comes actually out on our sockets. So that was very interesting. And then for the question here. So the synchronization overhead is clearly sort of per process. It's what's going on in the app at the moment. The bandwidth overhead is per system. And if I have a large number of processes running on the system, they're going to have to share bandwidth between themselves somehow. And it's clear that you could have a bad process that's eating all the bandwidth and basically starving other things out. You know, if you're in more than one socket system, people sharing across. Do you have any ideas or solutions on how you can track bandwidth system-wide and cooperate with other people who are also using bandwidth?
So that again is more like a part of my future work, and we have definitely given it enough thought. So something you can do is using a mechanism like this. Let's say we train on a particular application, and you generate a curve of how efficiently each application uses bandwidth using a mechanism like this. And then you can use an algorithm to actually split resources between the two applications based on a feedback mechanism like this.
Based on some efficiency metric. Okay,
Basically.
thanks.
Sure. All right, thank you very much.
Our second speaker is Michael Linderman. He's a PhD student at Stanford, one of Theresa Meng's students. He'll be presenting his work on Merge, a programming model for heterogeneous cores